Okay, I think we're going to get started. Thank you. Okay, so I think we're supposed to start at 20 past, aren't we? 20 past, good. Right, we're starting then. Lock the doors. Okay, no one can get out now. Thank you so much for coming along today. After sort of a very, sort of a sort of almost evangelical pitch for living on the moon, right? I'm now going to bring you crashing down to earth with the realization that you're really bad at patching your software, which feels like a bit of a journey to go on in just over an hour and a half. But thank you so much for coming along. My name's Sam Newman. We're going to be talking about microservice security. I've done some talks like this in the past. This is sort of a looking at some new ideas, building on some experience. We'll try and share with you a few tips for how you can think about security in the context of your microservice architectures. I've written a book in the past. Some of you may have read the book. If you haven't, you can go to a thing called the Safari Bookshelf, get a free trial, and read bits of that book for free. If you like it, then please do buy the book. I've got a house to pay for. I now run my own company doing training, advisory work, consultancy work, mostly based around Europe. And I'm actually in the process of working on a book around microservice decomposition. So monolith to microservice decomposition that should be out in the middle of the year. We're here, though, to talk about security, and I think we've become a lot more aware over the last few years around security concerns because we hear stories in the press. We hear of things like massive record breaches of taxpayer information, often in the US, which is quite nice when you're not there, but it happens to us too, but massive breaches like with Equifax. We're worried now about our chips, that the actual microprocessors that run our computers may actually have flaws. And we have all kinds of other issues around data and privacy in the post-Snowden era that give us cause for concern. And this comes at a backdrop where we sort of still think of security as an afterthought. We've moved on to this world where we're thinking more all-encompassing about the process of delivering software. We think about trying to build our design work, our user interaction design, our architecture thinking into our sort of tight design, develop, test and ship cycles. And we're sort of thinking, okay, about poly-skilled teams, everyone working together, reducing handoffs, shipping faster, and that's great. You know, we used to not do tests ourselves. We used to have other people write tests for us. And we realized, now if we do that, we can go faster. We used to have other people do usability design and pass down sort of chiseled in stone designs for us to implement. And now we realize the importance of interactive design and building that into the delivery process. But when it comes to security, we still sort of ghettoize it in a way. We sort of say that security is such a complicated topic that we couldn't possibly do anything with security. And so we leave it off to one side and we treat securing our applications as sort of a secondary activity, as a transactional activity, something that you'll do once a quarter. You'll get someone and hopefully they'll come in and sprinkle some security into your system, which is, I think, is a bit of a backward idea, the idea that only experts can help us here. There is a role for specialists in all fields. But just as with testing and, you know, we think about testing and DBAs and things like that, there's a role for having a great QA test specialist. There's a role for having a great DBA who really understands databases. But the idea that they do all the database work or all the test work is silly. We can do the low-hanging fruit ourselves and allow them to focus their time and energy on the really hard stuff. And it should be the same with security. I still think we're not where we need to be. What I'm hoping with this talk and others I've done before is to share just enough security. I'm not asking you all to become experts. I'm asking you maybe just to become maybe conscious incompetence, to be aware of what you don't know and to start maybe filling in some of those gaps. We're going to be looking at security in the context of microservice architectures, although a lot of the advice I will give may well be sort of more generic than that. But I am going to try and target the challenges that I see companies facing when adopting a microservice architecture. Now, on the face of it, microservices can actually help us a lot in regards to security. James Lewis always says that microservice architectures are an architecture which buys you options, and one of the options it buys you is more ways in which to defend your application and protect your data. With sort of a monolithic application, we have the all of your data is in one place problem. You've got a single monolithic process talking to a single monolithic database. This is kind of the most traditional type of application that many of you may well work on today. And we have this issue that one single breach breaches the whole application. If you get hold of the data set, you've got a hold of the whole data set. With a microservice architecture, hopefully we are more isolated. That isolation that we crave in order to allow us to have this property of independent deployability of our services can also help from a security point of view. By avoiding implementation coupling, we further protect ourselves. The idea being that we can focus our time and energy on those processes and that data storage that is most critical. We can worry a lot about where we store our PII because it's easier to spot where that lives. When you've got a big giant database and only a small part of that contains that personally identifiable information, you sort of have to treat the same data set as though it's all sensitive data. We start worrying about encrypting the whole thing, worrying about ingress and egress of any services that touch that database. With a microservice architecture, it can become much easier to sort of categorize from a security standpoint those services which deal with data which has increased privacy concerns. And that can be useful, especially when you're implementing things like the GDPR, because you can focus your time, energy, and attention in the right places. We also open up the possibility for defense in depth. We don't have to have, one big perimeter around our single monolithic system. We have multiple points with our sort of network hierarchy, our network topologies, where we could apply protections. The fact that we can mix technology stacks actually also can be beneficial to us. An exploit that might crack open an old process running Java 1.2, that same exploit isn't going to work against a Ruby on Rails stack or against a Go stack. And so actually having a mix of technologies can sometimes be a benefit in terms of maybe thwarting the impact of things like zero-day exploits. The flip side, though, with microservices is that, what they give and they also take away. Microservices architectures, on the face of it, also open us up to more attacks. A lot of information that used to flow within that single process boundary now flows over networks. And this actually is what attracts most people's attention when it comes to microservice security. It's really about network security. How do you ensure that the information flowing between services is protected? But what isn't often given enough thought is how do you restrict access to the endpoints themselves? And how do we think about protecting all of these machines? If you've got manual processes around patching and upgrading your machines, your services right now, and they might work perfectly adequately for a single monolithic process-based system, they will not scale in a microservice environment. And all too often, it's the basic stuff that I feel gets missed. And we are going to talk about some of the basic things first. So who here feels that they're pretty good at assessing risks? Now, of course, this is a leading question because I'm going to ask this question, hoping you'll put your hands up and then I'll prove to you that you don't know how to assess risks because you've seen talks before, you know how this works. But just internally, you can be going, yeah, I'm actually pretty good at that. And then, internally, I'll crush your feeling of confidence on your own abilities. So there's a really good report that comes out every year, the Verizon Data Breach Report. This looks at the Verizon's customers all across. Verizon are a telco in the US, and it's most looking at North American-based customers. But it has a really great, rich corpus of data looking at how breaches occur and what we can read into the ways in which breaches occur. This is slides taken actually from the 2017 report, which looked at the mechanisms used to break into systems. What attack vectors did malicious parties use to gain access to systems? And 81% of all the breaches they looked at related to either weak passwords that were easy to crack or easy to guess, or stolen passwords. A big subset of that is obviously social engineering, getting people to give you their password, right? But increasingly, this is just about having passwords that were easy to crack or easy to guess. So straight away, you think, well, actually, this is a fairly basic thing to get right. And unfortunately, we don't get passwords right as an industry. Both NIST and the UK Cybersecurity Centre, who are kind of, let's be really honest, traditionally, these are stodgy government IT agencies that seem to be about 30 years behind the cutting-edge trends of what we do in our daily practice. They've actually come out with some great advice around password management. Troy's got a really nice write-up on his blog. And they're talking about how they feel we should treat passwords for human beings and actual users of our systems. And some of the advice seems to be to maybe fly in the face of what is probably common practice at many of your organizations. So this is basic advice. Things like having a longer password is better. Longer is stronger. Longer increases entropy. I wonder how many of you have tried to create a password recently and you're told, sorry, your password can only be 12 characters long. I was buying a house recently, and because I was trying to buy a house, I had to open documents sent by a solicitor. That meant I had to sign up for an Office 365 membership. I felt like I was yak shaving at a certain point. So I had to sign up for my Office 365 account, and I think my password was limited to 16 characters. And I'm thinking, well, that makes no sense. Firstly, it's not a disk space issue, because passwords are actually hashed into a long hash. So why restrict the length of a password? Unless they are actually storing it in plain text. Microsoft wouldn't do that, would they? It's crazy. Allow people to do longer passwords, because if you make them shorter, and you insist on them being shorter, you have to require that the entropy comes from somewhere else. Where does the entropy come from? With shorter passwords? Yes, really complex character composition rules. Which lead to people being really confused about what makes for a valid password, because all of the requirements seem contradictory and you can't work out how to fit something into that model, right? And so you end up with passwords like capital P, ampersand, 55, W, uppercase O, R, and D, because it says password, right? And you can remember that, and that will be in every dictionary attack out there, right? So when you have complex character composition rules, what people end up doing is they come up with some standard formats that they know work for themselves, which are also quite easy to guess. So if you allow a long password, you can get the entropy without requiring these complex character composition rules. Third thing, have a password manager. Can you put your hands up if you use a password manager for your personal passwords? Right, probably about maybe a half to 2/3 of the room. Now put your hands up if you use password managers at work. All right, it's about the same. Oddly, some of the different people. So some people that use a password manager at work, but not at home, and at home, but not at work. It's very confusing to me. You should use a password manager. There is zero excuse for not using a password manager in this day and age. There really isn't. It allows you to generate unique passwords for each login that you use. It also allows you to very easily change those passwords if they need to change. Some of the good password managers, like 1Password, will even tell you if your password has been found in a breach file, so you can actually change those account credentials. There is no excuse. It's one of the single best things you can do is to embrace a password manager and use it for all of your things, especially inside your organization. This is the really controversial one for many people. Do not mandate password changes. How many people here at work every 6 months or so have to change the password for, say, their laptop? Or, yeah, look at that. Everyone does. And you know why we do it, right? We are made to change our passwords because people are worried that a malicious party is going to get access to your password. And so by requiring that you change it, you limit the impact if that password is found. But we're not changing our passwords frequently enough to eliminate that possibility, because we ask to change it every 3 to 6 months or so. What we are doing, though, when we constantly ask you, type in old password, type in new password, click OK. Oh, it's popped up again. OK, type in old password, type in new password. We are training everybody to basically be susceptible to phishing attacks, aren't we? Because now you log into work one day, a window pops up saying, you've got to change your password, put in your old password, put in your new password, and you want to get on with work and get some code built, and you've just given away your current credentials to some malicious party. So when you mandate password changes, far from making people more secure, you are training people to be more susceptible to social engineering. And so actually this is the UK government and the US government says, do not do this. Only require that passwords are changed when you feel that they have been breached. If you're using a password manager, you're going to have a unique password for that account anyway. And so if that password is found in a breach or is got hold of by a malicious party, you're limiting the impact of that. Moreover, it's easier to spot when these things become breached because you can target with these password managers now, like, 1Password works with Have I Been Pwned to say, yes, this is your credential, you should change this. Credentials are kind of interesting things because you also need to make it easy to change credentials and revoke credentials. And there are some credentials that you do want to rotate on a very, very frequent basis. A great example of this would be something like API keys used for accessing Azure or AWS. Here you're using programs to drive automation of your cloud infrastructure. You'll get an API key, you put it into your software development kit of choice, like Botto if you're using Python on AWS, for example, and I'll drive the construction of some part of my real estate or whatever else. In those situations, there's no reason for you to keep using the same API keys over and over again. You can regenerate those API keys on demand. Certainly, AWS allows for Active Directory federation, whereby you can generate time-limited API credentials just for you that will expire after half an hour and 45 minutes. You can then pass that into any program you run, do your automation. If anyone gets hold of those API keys, there's no problem. It's actually quite an easy thing to do. It shouldn't take a decent sysadmin more than half a day to do that kind of work. Why is this important? Well, how many people here have heard of CodeSpaces? Hands up if anyone's heard of. One person has heard of CodeSpaces. It's not surprising why you wouldn't have heard of CodeSpaces, because CodeSpaces, as you can tell from this rather graphic image, no longer exists. The graphic gives it away a little bit. What happened was, this was a company that provided secure source code hosting. It was a slightly ironic statement, secure source code hosting. Their application was deployed onto AWS, and a malicious party got hold of the root API credentials, the root Amazon account credentials, more to the point. And they wiped the entire production system off the face of the earth. Just deleted it all. I don't think they ever got to the bottom of who did it or how those credentials were leaked. There was some suspicion it might be maybe an annoyed ex-employee, or maybe someone just accidentally checked these details in. Not quite sure, but all wiped away, gone. But yeah, that's okay, you're thinking, Sam, because of course they had backups. And of course, yes, they did have backups. And where would you put backups? You put backups on the cloud, don't you? You put backups on the cloud in the same Amazon account. Now, when you talk about your backups being off-site, it's kind of, what it really means is the backups are away from the thing you're backing up. When both your production system and your backups are off-site, you need to still separate them. So putting your backups in a different Amazon account is a good idea. They did not. But that's okay, you're thinking, because surely they had all the source code for this system, so they could rebuild it somewhere else. Yeah, they had the source code. Anyone want to guess where it was? You get the idea. So there's also something here about not just limiting who has access to those credentials, rotating those sort of automation API credentials as quickly as possible, but also limiting the impact of what people can do if they get hold of those accounts. If they had segmented their infrastructure into multiple AWS accounts, you would have limited any one particular breach. This is the same idea as you having a unique password for each of your online identities. There are programs out there that you can use that will scan your Git repos looking for what look like checked-in Amazon API keys. More than one of my clients has lost money through this process. Because normally when people get hold of your AWS or your Azure API keys, they don't delete stuff. They might crypto lock you, but what's more likely is they're going to do some Bitcoin mining. So a few of my clients have woken up in the morning to find out that they've lost, say, $20,000 worth of Bitcoin mining. So that's much more common when people get hold of API credentials. Using tools like GitRob, for example, they can look over your Git repos and spot bits of text that look like they might be API keys. Amazon actually also do this themselves. They'll scan through publicly available repos looking for this stuff. It's very easy to have your API credentials maybe checked into some properties file that should be excluded from source control, but isn't. Next thing you know, you're being mined for stuff like that. It's also why it's a good idea to put cost controls onto your cloud accounts as well, to have alerts that go off and maybe hard limits, which are maybe within an acceptable tolerance of what you normally use. So rotating of some of programmatic credentials like Amazon API keys and database credentials is really useful. But that's enough of a pain with a monolithic system. We start thinking about a microservice architecture, this becomes really problematic because we don't have one machine or one text file where I have to change a value. There isn't one place where I can just inject these credentials in. I've got multiple services rolling around here. I've just got 6 services, but each of these services will probably be deployed on at least 2 separate machines, maybe 3 or 4. And there's a whole load of different shared secrets that I might have floating around this system. They could be everything from private public key pairs, Amazon API key pairs, database credentials, all these other types of things. You might be using sort of API keys for HMAC and stuff like that. And I start thinking, well, how do I rapidly rotate those things or revoke those credentials when I'm worried that someone may have got access to them inadvertently? This is where having a proper secret stores can help. Because I've got I've got a text file that sits on that machine. It's got my admin, and here's my administration password for that database and some lovely password there. Someone gets hold of that text file, I'm in trouble, right? So if you can constantly rotate those things, and that's actually a key part of protecting yourself, is rapidly rotating these credentials. The problem is when it's a manual process, we tend to do it once a year, and then we forget. But if we can fully automate it, it becomes something that we can do on demand daily. And that's a huge win for us. So one of the ways that we can do this is using something like secret stores. So there are a bunch of different secret stores out there. There's a very basic one built into Kubernetes, for example. Both Amazon and Azure provide variations on the secret stores. So I'm a big fan now of a tool called Vault, but you've also got things like the Key Management Service and Parameter Store on AWS. Vault is really interesting. It's something you can deploy yourself because it has a whole bunch of really advanced capabilities, and it already has built-in support for automatically generating credentials for backing services. The way Vault works is pretty straightforward, really. What it can do is it can talk to a database on your behalf. So it can talk to AWS on your behalf. As an application, you say, "Can I have my database credentials?" So the application has to authenticate itself with Vault. And Vault says, "Okay, right, yes, you can. I'm going to go and create your own username and password, and I'm going to pass it back to you." So now it's not just this one application. It's this one application instance can have its own username and password if you want. If someone gets hold of that, you can more easily revoke that. It will also make sure that these credentials are time limited. So every 45 minutes or an hour, those things can expire, and it can update you and say, "There's new credentials for you. There's new credentials for you." And Vault can do all of that for you, automatically rotating programmatic credentials. You do the same thing with things like AWS API keys. And this sort of pluggable nature means you can plug in your own back-end infrastructure. If you've got your own custom services that you want to generate time-limited credentials for, it's not super hard to do that. You can also use Vault as a way of doing this for human beings as well. If your QA wants to go and maybe run a quick read-only query against their production database, not that they should be doing that directly, you could actually generate them a username and password that's only going to work for the next half an hour. And then it will be expired. So things like Vault are really interesting. Vault also works really nicely with a tool called CONSUL template. CONSUL template sounds really dull, but it's the kind of tool that gets me really excited. It updates text files based on what's in Vault, or what's in a tool called CONSUL, which is a configuration and service discovery system. That seems really, really boring. But think of all the programs you've got that read their configuration from text files. You don't have to update them to start calling out to some fancy new secret stores. Instead, you say you don't. Keep reading your configuration from a text file. What you can then do is have CONSUL template update that text file as that information changes. Your database username and password pair expire, it automatically updates a text file that you're reading locally. And so your programs don't actually even have to be aware that this is going on. It's completely opaque to them. I think there's also a similar tool that does the same for environment variables, although you shouldn't probably really be injecting secrets in as environment variables, but that's a separate thing entirely. So secret stores are really, really useful. Probably overkill for simple applications, but as your microservice architecture becomes more complicated, you're probably going to be looking for centralized configuration management anyway. Having a secret store as well is really, really useful. The secret store that you get with Kubernetes is not fantastic. It's getting better every release, but it still lags a long, long way behind Vault, which I think is the best thing that HashiCorp have ever done. What else causes breaches? There's another report back. This is 2016 now. I need to refresh some of my references. But here they found, this is a Forbes BMC report that found that 44% of all serious breaches occurred after vulnerabilities had been identified, but those vulnerabilities had not been patched. In other words, they found a problem, they didn't do anything about the problem, and that problem caused them to have this data breach. So in other words, this is, you knew this could happen and you didn't do anything about it type problems. This is embarrassing. An awful lot of this is down to patching. So some of you may have heard of a company called Equifax, who lost a large amount of their information due to a breach in a web application framework called Struts. Now, Equifax are a credit reference checking agency. That means they have to store a lot of information about their customers to do your credit scoring. So in the US, this would be, your name, your address, your family members, your date of birth, your social security numbers, all the places you've lived at, all the credit cards you hold. You get the idea. I think it was something like 160 million records were stolen, and a lot of them did affect people in the UK and elsewhere in Europe. The story behind this is kind of all too familiar, but it's a good example of the challenges that we face in this area. So the vulnerability that caused this data breach was, as I said, in this library called struts. Here it is. You see it on the critical vulnerability, the CVE database. And it has this score, the CVE database has this score called the CVSS severity. So this just tells you how bad this exploit is, right? How bad on a scale of, 0 to 10, how bad this thing is. Now, as you can see here, this particular vulnerability has a 10. Now, that's not at the good end of the scale, and as I mentioned, it's not out of 100. It is out of 10. So there isn't a worst possible vulnerability that you could find. What it basically allowed is for easy remote access to all of this information. Now, this particular defect was reported in March 2017, and this is common in good bug reporting sort of behaviors. They'd already spoken to the team who wrote struts, and the team were already ready with fixes and bug fixes. And so they announced this is a really serious problem, and the patches are already available at the same time. So I want to make it very, very clear this is a problem. So this was March. I think it was March 7th is when the patches were made available. So let's talk about what was happening meanwhile over at Equifax. So over at Equifax, they realized that between mid-May and July of that self-same year, they had a massive, massive data breach. They're not sure when the breach occurred, other than it was somewhere in this window. Not exactly sure when. They spotted it at the end of July. So they only realized in July that someone's nicked loads of our data. They then reported it publicly on September the 7th. Now, I don't know if anyone can see anything interesting about these two dates. And the thing I'm immediately drawn towards is the fact that they're a long way apart. So, there is no GDPR equivalent in the US. There is no requirement for mandatory data reporting of breaches in the US. They don't have to tell you. If they think they can get away with it, they will try. There's also an interesting thing that a bunch of Equifax executives dumped a load of their stock between these two dates, which I'm sure was completely coincidental and it implies no impropriety on their part, and it's definitely not insider trading whatsoever, although I know people are investigating this. So we know, based on what all happened here, that when the breach was discovered, there was the patch had been available that would have fixed this problem. That patch had been available from anywhere from 2 up to 4 months. So they may have had up to a 4-month window in which they could have installed that patch and defended against this breach. But worst case, it was 2 months they had between the patch being available and the breach happening. 2 months. That's a long time. How many people here are confident that they patch all of their software and that at least they apply all the patches every 2 to 4 months? How many people are confident? Yeah, patches. How many operators? Put your hands up if you think you can do it. Right, come on. Yeah. No, you don't. Right, so let's talk about patching. Because the reality is with microservice architectures, we don't have simple deployment topologies anymore, do we? Oh, no. We're sort of on this sort of tottering tower of interrelated dependencies and virtual machine abstractions. It's like some kind of nasty, rotten Russian doll situation where we're hoping all of the dolls are kind of good and being looked after, but someone else is doing it for us, so we have to trust them. Here we are, we've got your underlying hardware. You remember, these are real computers, right? We don't tend to deal with these directly anymore. On top of those real computers, you're running an operating system. On top of the operating system, you are running a hypervisor. This is a type 2 hypervisor. So this is things like your VMware, vSphere, KVM, Zen. When you use a managed virtual machines on most of the cloud providers, this is the kind of stack you are deploying on. On top of the hypervisor, you've got the virtual machine operating system. On top of the virtual machine operating system, of course, you're running Docker. I mean, who wouldn't run Docker? And on top of Docker, you've got the operating system that runs on top of Docker, because you do run full operating systems inside Docker. And on top of that, you have your application. Now, it's worth noting that the struts problem was identified in that little tippy-toppy bit up there. It's one place. But every single level of that stack needs patching. Every single one. We're now even having to roll out patches for our chips. You remember with Spectre and Heartbleed? We knew Spectre Meltdown, we had to roll out patches for that stuff. So this is, if you're running, say, a container-based system, this is what your deployment stack looks like. So how many of you are still confident that you have all of those layers patched every 2 to 4 months, including every single one of your developer dependencies? One person. I will high five later. Right. That's not unsure. And a lot of you think you might, but you're not sure, because we lack visibility, actually, a lot into what's happening in these layers of the stack now. They are hidden from us. Even if you're running on-premise on our own private cloud, it's different departments and different people that handle different layers. So there is a bit of a trust thing going on. So what can we do about all this? Well, the first thing is, if you run on a cloud provider, you don't get the option to be involved with part of it. And so, if you're doing managed VMs on, say, Azure or AWS or Google, they are going to handle this for you. This is the infrastructure as a service level. They are going to patch and manage your VMs. The operating system running on that VM is still on you, of course, to patch and look after. If you are using sort of a more highly abstracted service from the cloud providers, you may be using EKS or some similar container platform, say a managed Kubernetes instance or maybe a managed Cloud Foundry. Pretty much at this level below is being looked after for you. So Fargate is well in here. The cloud provider is saying, we will handle this. And we know they do, right? They do a very good job because they already have the skills at managing this stuff at scale. When Spectre and Meltdown came out, they patched all of those chips within a week, all the public cloud providers. They'd applied the underlying hardware, firmware patches within a week. We know that because all of our machines got 30% slower within a week, right? That's how that worked. But why didn't they do this? So then this is your responsibility. This is your responsibility now. It's just these two little levels. This is two little things. So now your operating system running your Docker container and, of course, your own application stack. Now, with microservices, this kind of gets interesting because if you build a service that does one thing and does it well, whatever that means, you deploy that service into a production environment and it doesn't need to change for 6 months. Guess what? It's been running for 6 months. You don't log into and patch that container. That's not how that works. If you're going to roll out new operating system patches, you have to redeploy that. And if you haven't in the last 6 months, that's a 6-month window where patches have not been applied. And as you get into finer and finer grained architectures, that is much more likely to happen. And so it doesn't matter what you think is happening in source code, it's actually what's happening in production. Now again, if you're using an even higher level abstraction platform from a cloud provider, maybe using function as a service, you can just focus on your function at this point. You still have your own developer dependencies to worry about. They still wouldn't have saved Equifax because they'd be running struts up here. Now, there are tools that can help. You've got open source tools that can start helping us in the area of looking after our containers and our functions. You've got things like Claire, which is all right, comes from CoreOS, which does sort of looks at vulnerabilities in Docker container images. It does start to struggle a little bit under once you get a sufficient volume of containers and things. I would tend to look towards something like Aquasec, which is a really good tool for looking both at sort of build and deploy time and runtime vulnerabilities in your container images. So it can say, well, these are the containers you've got, here are the vulnerabilities we're seeing, you may need to do something about it. So it's well worth a look, have a play around with that tool if you're worried about this stuff. For developer dependencies, the tool I like the most is a tool called Snyk. So Snyk, the team actually happens to be based out of the UK. Snyk's a really quite simple tool. What it does is it looks at the dependencies that you declare for your third-party libraries. And so it supports different languages, supports .NET and Java and Ruby and Python, I think. And so it will understand your Maven files or your NuGet dependencies and all these sorts of things. And it says, oh, well, look, you seem to depend on version 1.1 of awesome YAML parser. We know, because they actually curate a big database of vulnerabilities, we know that YAML awesome parser version 1.1 has a real big issue that can allow for arbitrary code exploitation, arbitrary code execution. So you need to patch it. They'll let you know, they'll tell you, there is a vulnerability running here. They'll go a bit further than that, and they'll actually send you a pull request changing your dependency files. You can upgrade to the latest dependency. You just have to click a button. You go, OK, I'll take that new change. You can actually build that into your build process. Your builds can fail if you depend on any libraries that have known vulnerabilities in them. So now suddenly you can't even deploy the code until you upgrade that. And Snyk have been increasing that. They've gone from just the build time stuff, they're now doing runtime support, looking at even your functions and things that are running as well, which is really powerful stuff. It's not that expensive, it really is, and it will save you an awful lot of money. Think about how much money it may have saved Netflix, for example. Now let's move on and talk a bit more about some of the networking related stuff. Not Netflix, I said Equifax, anyway. Let's move on now and start thinking about some of the challenges related to sort of service-to-service communication, because I think that's what people get really interested in. Now, I would say, I would focus on some of those. Getting your patching hygiene right and your password hygiene right are like, they're table stakes for this stuff. I think people start rushing to all the really complicated, let's worry about JOT tokens, and they're sort of leaving the big giant back door open in their house. It's like, no, you've got to close that back door first. But let's talk about these other issues around things like network security and sort of inter-service authentication and authorization concerns. So we'll take a look at a very simple architecture here. It's just 4 services running inside our perimeter. We're talking maybe upstream to a couple of user interfaces, a couple of devices, maybe a native mobile application, some kind of web-based application. And we're also talking to some downstream party, sort of an external to us, but maybe a trusted party with sending sensitive financial information. So, here we are, some sort of big streaming company. And the thing we're worried about, of course, we've dealt with all the other issues. We're starting to worry about these lines. And we're starting to worry about all of this sort of, we've kind of increased our surface area of attack. So how do we defend ourselves? We start thinking about things like transport security. There are kind of 4 key concerns that we need to address. The first is, are we worried and can we restrict the ability for people to observe data in transit? So can they see information being sent between our services? The second thing we're concerned about is, if they can see the data, can they manipulate it? There are some mechanisms you can use to make it easy to see, but not easy to change. I mean, HMAC over HTTP will do that, for example. We also need to restrict access to the endpoints. So it's all very well protecting the bit of the pipe between 2 services, but if we allow anyone to talk to a service, we haven't really helped that much. And we also need to potentially stop people masquerading as endpoints. This is quite a niche thing. But a smart malicious party could launch a service saying, oh yes, I am the payment service. Please send me requests. And you start sending it credit card information, right? Again, I don't see this happening, but it's a theoretical possibility. So these are the sort of 4 concerns. So I'm not going to go through all the different networking options out there, but I will start talking about really the most popular networking protocol used for service-to-service communication. And this is one we either use directly or indirectly through the use of things like gRPC, and that's HTTP. And so with HTTP, people immediately gravitate towards saying things like HTTPS everywhere. What I mean is HTTP and TLS. Now that makes perfect sense for the public internet. And there's a lot of value in having that for the public internet. And there's no excuse for not doing it. And if you think you have an excuse, I suggest you go talk to people who know more about that sort of stuff, but because you don't. So HTTP and TLS is where the server, basically, you're running sort of TLS from the server side. So clients go to a known server. I know you are who you say you are. But that TLS also protects the data in transit. So what we do is we get server guarantees. The server I'm talking to is the server I know it should be. So I'm not accidentally going to something that's claiming to be a service. So I'm dealing with that impersonation of endpoints. I can also get guarantees that the payload itself has not been manipulated. I'm effectively protecting myself against a man-in-the-middle attack. We don't have necessarily any client guarantees just with server-side certificates. So that's something to think about. If you just have server-side certificates with HTTPS, any client can still access your service. So that could still be somebody who's logged onto a machine on your network running curl, putting down all of your customer data, but over HTTPS, so that's good. And certificate management historically was something people complained about. I think the arguments around certificate management are pretty weak nowadays. Firstly, if you're building a microservice architecture, you are automating things. And if you're automating things, there are lots of tool chains for managing the rollout of server-side certificates. Obviously, for the public internet, we have Let's Encrypt, which everyone went crazy about because they're free. Oh, it's free. That was never the point with Let's Encrypt, because it wasn't the $40 fee from Thwaite that was putting you off installing a server-side certificate, was it? It was the fact it was a manual process. So Let's Encrypt is fully automated. All the cloud providers allow you to issue free certificates for this sort of stuff and give you a tool chain for managing those certificates and changing those certificates in a fully automated fashion. They charge you zero money for this stuff. So I use AWS Certificate Manager for some of my public-facing stuff, right? And I just write a program, and every now and then it runs and I update my certificates. It's easy stuff. So this is OK, server-side certificates for TLS. It sort of helps us around observation of data. It helps us around manipulation of data. It doesn't really necessarily, unless we augment this, help us around restriction of access to endpoints. And it does, though, stop us impersonating endpoints. This is a good start, and as a result, as a sensible default choice. Definitely for maybe your public side communication with the outside world, because here we use another technique for client-side authentication. We're going to use human being information to say, who are these people? Inside our service architecture, we do have to deal with the client-side issue, though, because we need some way of authenticating these people who are allowed to access our endpoints. So this is where we start talking about mutual TLS, where both the client and the server use certificates as part of this handshaking process. So basically, we both have our own certificate. This is lovely. Now, the problem here is, OK, we get client and server guarantees. We've solved most of our issues now. But certificate management here is much more painful, often because you have more consumers than producers, and also because the tool chains here aren't as good historically. I have used things like Puppet and Chef to roll these certificates out, and it's not much fun, although the solutions in that space have got better. Again, on the public cloud platform, your life can be much easier. It took me all of 30 seconds to find about 5 different articles on using the Azure API Gateway for managing client-side certificates, for example, and this is just one example of the articles I found. So this is an easy process to do if you're using those API gateways. There's also something you can do now with service meshes, which I think will be probably the long-term way we solve these problems going forward, although those solutions aren't necessarily as mature as they could be. So mutual TLS is great, right? Mutual TLS, helps us around observation of data, make sure the data isn't manipulated, restricts access to that data, and stops people impersonating endpoints. Isn't that fantastic? And again, let's do this everywhere. Even if I had to manually manage the client-side certificates, I would still strongly consider using it for things like accessing, talking to trusted third-party systems over the public internet. And you can sort of handle that certificate management using things like Bastion servers, which can reduce the overhead of having to revoke those credentials and things and change those credentials. Other protocols, of course, you may well be using, not using, say, synchronous over HTTP. You might be using some kind of communication over a broker. You might be using Kafka. You might be using RabbitMQ. In those situations, you're going to have to look at your own documentation of your vendor to find out what protection of the network traffic they provide. Both Rabbit and Kafka have very good solutions in this space. Pretty sure certainly Rabbit actually does TLS for its transport. And there are additional ACLs and RBAC type stuff for accessing topics and queues and things built on top of that, which ensures that you can share this infrastructure across multiple teams and restrict which teams can see which queues and which topics as well. And those are both things that Kafka and Rabbit have. I'm sure most other modern brokers will have similar capabilities. So this is great, because so far what we've dealt with is the transport authentication problem. We've dealt with server-side identity, client-side identity. We've sort of solved the problem to an extent, or we've talked about the problem of how one computer talks to another computer. The problem is, if it was just computers talking to computers, A, the system wouldn't be that useful, and B, it would also be a lot simpler, because we also have human beings to worry about. And that's where things get tricky, because human beings require we've got to think a bit differently about them. So in these situations, when we're thinking about our upstream clients, we're thinking about our native mobile clients, our web clients, people are going to log in, and they're going to say, I would like to see my account. And normally you'd use some kind of thing running on the perimeter of your system that will handle your sort of authorization. And so I logged in, and I'll say, can I access a site? You get redirected, and I have to provide my credentials. It drops a cookie or something in local storage, and then when I come back to the auth gateway says, yes, that's a valid cookie. You are now authenticated, and you can access the rest of the system. And so there's different schemes you might use for those kinds of things, OAuth and basic auth and things like that. And the whole point of these auth gateways is you can kind of make the assumption then that once anything gets past it, that all the users that have got past it have been authenticated and are actually real people that we at this point trust. And those auth gateways will also do things like handle expiring cookies and redirection if you have to log in again. Right? Very, very, very standard stuff, this. So this is kind of nice. Only authenticated users get through here. Of course, we've got the bigger issue here. It's not authentication, it's authorization. So authentication says you are who you say you are. Authentication is you are allowed to do what you claim to want to be able to do, restricting what you're allowed to do based on who you are. And authentication is kind of more tricky. So authorization is kind of more tricky. So let's go through a simple flow. Bob logs in, says, hi, I am Bob. And the auth gateway says, really, prove it. And so I get redirected. I have to enter my information in some sort of login field. And I said, yes, I really am Bob. You can tell because here's my password, capital P, @55W. I type that in, and the auth gateway says, OK, fine, you're allowed in. So now I am considered, I've authenticated myself. I am who I say I am. And so now my request to say view my profile page in this example is allowed to go forward, and the music web shop says, well, I can almost at this point work under the assumption that the request being made here is coming from a user who has authenticated themselves. The challenge is authentication is not authorization. So let's consider what I mean by that. So here's the auth gateway. I say, I want to access my profile page. So I click on a link, and that takes me to /user/Bob, and that's going to present a nice HTML page with information about me, where I live, maybe the orders I've placed in the last 6 months, that sort of information. And so I make that request. The auth gateway says, well, you're logged in, so that's fine. I'm going to pass that request on, because I don't handle this page. Somebody else handles this page, and the thing that handles generating that profile page is the music web shop. And the music web shop starts putting that page together and realizes, this information here I don't have. That information is actually a downstream service's responsibility to generate. Very common scenario in a microservice environment. So the web shop goes off to the user service and says, dear user service, can I please have Bob's data? Now at this point, we're in a world of implicit trust. We've maybe used our network-based authentication and authorization. And so the user service and the music web shop have established a level of trust. And most people are, at this point, embrace implicit trust. In other words, at this point, the user service is going to trust anything that comes from a known upstream service. So the music web shop says, can I have Bob's details? And the user service says, well, you're the music shop. I trust you. You wouldn't ask me to do anything I shouldn't do. So of course, here is Bob's information. The music web shop takes Bob's information, puts it in the web page, and serves that web page up publicly. And so far, nothing's actually gone wrong. So Bob gets Bob's information. Now, as we know from all these papers on sort of security issues and AppSec engineering and the like, Bob is always up to no good, and he's always trying it on. And so Bob looks at that URI and thinks, hang on, there's my username in there. I wonder what happens if I take out the word Bob. What if I try accessing Alice's data? I put Alice in there instead. This is a bad URI scheme for a number of reasons, but anyway. So I come to the auth gateway and said, I want to make this request. The auth gateway says, I don't really handle requests, but I'm not going to let that request proceed until I know you're logged in. But look, you've got a cookie, you're logged in, great, off you go. So the request goes downstream to the web shop. The web shop says, you want some information, but I don't handle that information. The user service, that's where I go to get user information. So I'm going to make that request downstream. Can I have Alice's details? I'm being asked for Alice's details. And the user service goes, well, of course you can, because you're the web shop. I trust you. You wouldn't do anything you're not supposed to do, would you? We went to school together. We grew up together. Right. So back comes Alice's details, and now Bob has basically accessed Alice's details. Effectively, what we've done is we've tricked an intermediary party into asking for things it shouldn't be able to ask for. And the downstream service has just assumed that the upstream service is doing the right thing. So this is an example of what some people call the confused deputy problem, right? You've literally confused a deputy between you and the downstream party into sending back information it shouldn't, or doing something it shouldn't be able to do. You can also call it a confused proxy problem as well. Now, what we want to do, really, is some sort of authorization. So the normal solution to this problem is something has to say the request that user, that human being is making, has to be authorized. So I have to know what it is that you, as Bob, can do. And so something somewhere has got to have the logic that says Bob is not allowed to ask for Alice's information. In fact, the only information Bob can ask for is Bob's information. The question, of course, is where do you make that decision? Now, we could have that decision made upstream, here or here. But let's think about this as a microservice architecture. We're breaking apart functionality. We're pushing functionality out into services. So we're asking an upstream service or an upstream gateway to know what functionality you might be using of downstream services at some point later in this call, and also to know how you're allowed to use those things. So you're sort of doing centralized authorization upstream for capabilities you might perhaps use later on downstream. How is a gateway here supposed to know that this request might ultimately result in a call to this service downstream? I could get a bit closer by doing it here, but again, where am I going to store that information and how am I going to know what calls are going to be made? What if the user service makes a subsequent call downstream that also requires authorization of that human being? We've got two problems, really. One is, where do we make that decision? And the second is, how do things downstream or upstream make that decision if they don't know who the user is? So we also need to pass context of the user downstream as well. Now, ideally, when we're thinking about a microservice architecture, as we're pushing responsibility into the services, making those services more autonomous, it'd be better, rather than making decisions upstream on downstream services, it would be much nicer if the downstream service was allowed to make that decision. Because if you think about it, you create a service, you add a piece of functionality, it would be nice to not have to then go to some other service to configure the authorization rules for that. It would be nice to do that in the service you just created. For that to work, the downstream service needs to know who is the user. So we've got to work out how to pass that information downstream. What we'd like is for the user service to go, hang on a minute, you are Bob, you're asking for Alice's information, and I know, based on my logic, that that is wrong. And no, you can't. That's the dream. This is how we solve this nowadays most commonly with something like JOT tokens. So a JOT token, or Java JWT token, is a mechanism of taking information about a user, encrypting that information, hashing that information into a token that can be sent and passed downstream in a series of calls. You can send that from HTTP to HTTP to HTTP calls. You can send that over message brokers, whatever else. And so when I come in to make that request into the system, I generate a JOT token for the scope of that request that contains information about the person making the request. Downstream services can verify that that token is valid without any additional round tripping needed. So no calling into a central auth server is required. So the tokens look, I could create a JavaScript, set a JSON payload like this, have arbitrary name value pair information. So in this example, I've just put an ID and the name of the user, and that will generate me something like this. This is actually the header, the payload, and the signature. So downstream services can just use public keys to validate that this JOT token is actually valid and correct. And so the only thing you've got to deal with then is how you communicate those keys out of band. So in this example, the way you deal with this is I come in and maybe I've logged in, and so I've got some sort of OAuth token, or I've got like a cookie representing my logged in state. The auth gateway says, great, you are Bob, so I'm now going to generate a matching JWT token inside my perimeter, because a lot of the time you want those JWT tokens to be short-lived and not to contain, and you might be able to put information in that JOT token that you don't necessarily want to let outside your perimeter. You generate a JWT token that contains maybe something as simple as the user is Bob. That token gets passed downstream, could be in the header of the request. The user service gets asked, can you give me Alice's details? The logic in the user service says, I will only give Alice's details to Alice. It takes the token, validates it's a real token, extracts the information, it sees the user is Bob, and it goes, no way. That's not going to happen. So that sort of solves some of our parsing the identity downstream issues. And obviously, you can imagine passing that JWT token down to a number of series of different calls. There are some limitations of this approach. Firstly, if you've got flows that might last 5 days, right, you might be kicking off some backstream process. Do you generate a JOT token with a 5-day validity? That can be a bit risky. Secondly, you need to make sure that people don't get hold of those JWT tokens, just like you don't want to get you don't want people to get hold of your session cookies, and so you have the same issues there. Also, size. I spoke to at least one client who was doing rights management for music, and sort of actually literally was streaming around music, and they have incredibly complicated rules in some situations around who can access media, for example. So, you're in Azerbaijan on June after 10 p.m. and you can't access the record, something crazy like that, right? And so they did sort of a back of the napkin calculation and said, well, the information we need for our music rights management to know whether or not you can see a track, we would have to generate, the JOT tokens on average would have like about 10,000 fields in them, which is clearly insane. So in that environment, what we suggested doing was using these JOT tokens for the bulk of stuff that was much more simple in terms of their authorization schemes, and instead only then relying on a centralized server for that really complicated case. Some people I do know actually put the JWT tokens up on the client device. It doesn't feel right to me. It feels like it's an internal request scoped concern, but your mileage may vary on that stuff. So JOT tokens can be useful. They can be they're quite widely used now. Most programming languages that are used for microservices have support for generating and reading JWT tokens. There were some initial gotchas and some exploits reported around them, but they're quite widely used now. I don't think this is the final answer on this stuff. I just think it's the best answer we've got right now. I did mention earlier some technology around called service meshes. Service meshes are kind of an interesting idea, especially for those of you who are deploying onto Kubernetes. They effectively means that when you're communicating from service to service on Kubernetes, that your communication goes via effectively local proxies. Those local proxies can be configured and managed by you, and they can actually handle things like mutual TLS, JWT tokens, and all those sorts of things. Because those proxies are guaranteed to live on the same machine as you, the communication between your service instance and the proxy runs over a local network, so it's much less vulnerable. And those proxies give you a centralized place for handling the revocation of things like certificates and API keys. If you're interested in service meshes, you may want to take a look at things like Istio. There are sort of different programming models out there, but it's kind of really interesting. This is sort of how Linkerd works. Istio works a bit differently. So if you are on Kubernetes, you may want to take a look at that. I think if you can, for companies at scale, service meshes have the potential to simplify a lot of our inter-service communication concerns. Certainly for synchronous calls. They don't really do anything for you for async. This is really about synchronous and predominantly HTTP synchronous calls. If you can delay a decision about a service mesh for 6 months, that would be great because they're still maturing. I've been given that advice the last 2.5 years, by the way. Right, anyway. We are more or less at time. I've got a couple of minutes for questions, but I just want to say thank you so much for having me. I hope you enjoy the rest of the conference. Just to summarize, patch your stuff. Think about passwords sensibly. Consider secret storage. Especially you're operating at scale, things like Vault would be a good idea. Transport security is fine, but it's not the be-all and end-all. You also need to consider how you deal with humans and how you handle about authorization flows and passing those things along. And finally, you might want to consider service meshes, but that's probably only for the Kubernetes crowd right now, and only then if you're okay with some bleeding-edge tech. So anyway, thank you so much for your time. And there's loads more videos on my website about security and serverless and stuff if you're interested. Thank you.